My name is Robert Watts. I'm an independent digital design consultant, but I do all the digital design work for Chord Electronics. I'm here today to talk about the Hugo TT2 and to give you publish some of the measurements that we've recently extracted from the TT2. So, time domain. The primary purpose of a DAC, most people think about DACs as something that reproduces digital data. And it's not an unreasonable assumption to say a DAC is there to reproduce digital data. The thing is, a DAC is not there to reproduce digital data. The DAC is there to reproduce the original unsampled analog signal that was in the A to D converter. And this is fundamentally a very different approach to most DAC designers because they think entirely about reproducing digital data, hence the popularity of NOS DACs when all they do is keep the original digital data. The problem with this approach is that what the DAC has to do is to reconstruct the original analog signal, which is the signal that was from one sample to the next sample. Now, with CD, you've got 22 microseconds delay. And the DAC has to reconstruct, through the interpolation filter, exactly the analog signal, the bandwidth-limited analog signal that was in the A to D converter. Now, if you look into the theory, behind sampling theory, it's very clear what you need to do in terms of recovering a bandwidth-limited signal. And that is to use a sync function. Now, a sync function will enable you to perfectly reconstruct the original bandwidth-limited signal. So when you go from one sample to the next sample, it will make no difference whether you were sampling at 22 microseconds or 2 femtoseconds. You would have exactly the same waveform. The trouble is, conventional DACs are very poor at reconstructing the original waveform, and there are errors in terms of timing. So the signal will be either slightly in front or slightly behind where it's supposed to be. And this is a big problem for transients. And transients are very, very important from a psychoacoustic perception point of view. The reason why transients are very important from a perception point of view is that we use transients to do a number of things, or the brain uses transients to do a number of things. One thing is bass perception. The ear is very poor at reproducing bass. And what the brain does is it calculates what the pitch of the bass actually is from the starting transient. And they've done experiments where they take a bass guitar, they remove the original plucking sound of the bass guitar, and then they find out that people can no longer tell the pitch of the bass. The other thing that's interesting is that if you listen to a piano or a trumpet, the timbre of a piano and trumpet is obviously very, very different. One sounds very bright, the other sounds very different. If you remove the starting transients of a piano or a trumpet, it becomes very difficult to tell the difference in sound between a trumpet and a piano, even though that their timbral color is very, 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 very different. So the perception of timbre depends upon accurately reconstructing transients properly. The other thing that we know, of course, is that transients are used, or the timing is used from left to right to accurately locate instruments in space. And that's part of the interaural delay. And we know that the brain is capable of resolving something like 4 microseconds in terms of how the neurons are firing for the interaural delay. So timing from the left to right is very important to locate sounds in space. So what have we done with Hugo TT2? I've got a much bigger WTA interpolation filter. This means that it's much more accurate in terms of recovering the original transient information correctly. In the TT2 case, we've got 98,000 taps. That means that we can guarantee the reconstruction is better than 13 bits. And you may say, oh, 13 bits, that doesn't sound very good. But conventional DACs will only manage 2 or 3 bits worth of reconstruction accuracy. This is around 5 times better than the original TT DAC that I originally designed. The next WTA filter then takes us to 256 FS. So the first WTA filter works to 16 FS, which is about 1.6 microseconds. And then I go from 1.6 microseconds to 88 nanoseconds using a WTA interpolation filter. And I found that made quite a big difference to the sound quality, in that you could perceive the starting and stopping of notes much more accurately. Then there's more interpolation filters going from 256 FS to 2048 FS. We've also got, like Hugo 2, the options to change the filters themselves. So you can have a slightly softer sound, or you can have a more natural, incisive sound quality. Noise floor modulation. Now, if anybody's attended any of my talks or watched me on Headfire or anything, noise floor modulation is something that I go on a lot about. And it's actually very crucial to performance. What is noise floor modulation? If you take a signal, a very small signal, say at minus 60 dB, and measure the noise floor, you'll see the noise at conventional DACs between minus 160 to, say, maybe minus 180 dB. When the signal increases, the noise itself increases. So the noise floor pumps up and down with the signal. Now what I found is that the brain is very, very sensitive to any kind of noise that is signal dependent. So it's a bit like a sound of a saxophone. If you've got a sound of a saxophone, it's very rich and very dark. If you have a white noise, which is hiss, pumping up and down with the sound of the saxophone, the brain can't tell the difference between a saxophone and the hiss. And so it lumps the two together, and it makes the saxophone sound much brighter than it should do, because it's got this noise that's pumping up and down with the saxophone. And it can't separate the sounds out. What I found is that the brain is incredibly sensitive to this kind of noise floor modulation. And you can even have undetectable or unmeasurable levels of noise floor modulation, reduce the noise floor modulation, and you hear improvements in terms of warmth and smoothness. So this concept is very, very important in terms of DAC design. The problem we have with DAC design is that noise floor modulation is a huge problem. You can get it from jitter, you can get it from the architecture, you can get it from RF noise, you can get it from the analog sections. There are a hideous number of ways of creating noise floor modulation. So trying to eliminate that noise floor modulation has been something that I've been working on for a very, very long period of time. And I'll be showing you the results later we got with TT2. So what have I done to reduce noise floor modulation? One of the things is the use of Pulsar DAC technology, which is an architecture that I created in '95. One of the benefits of Pulsar is that it combines the benefits of DSD, but without any of the disadvantages of DSD. One disadvantage that DSD has got is that the noise modulators intrinsically create noise floor modulation. So you can eliminate the problem of the noise shaper creating noise floor modulation by using the Pulsar strategy. The other benefit is that as an architecture, it's completely jitter insensitive, or relatively jitter insensitive. What people don't appreciate is that you can design a DAC to suit any jitter requirements that you've got. In fact, there's one silicon chip design that I was working on where the original specification said we want it to work with 4 picoseconds worth of random jitter, and we want 120 dB performance. I said, fine, we can do this. Here's the design, after a suitable period of time. They then turned around and said, oh no, we've got our calculations wrong. We want it to be 15 picoseconds worth of random jitter, because we think the clock activity rate is going to be pretty poor and there's going to be lots of corruption from inside the chip. So I said, fine, okay, we can change that. Here's the new design. And the new design will work to 15 picoseconds with that level of performance. So you can adopt the DAC architecture to suit the jitter requirements that you've got coming through. This is something that you can do with Delta Sigma DACs. It is impossible to do with R2R DACs. R2R DACs are fundamentally jitter very, very sensitive. So getting rid of jitter is a major issue, and one of the major issues is noise floor modulation. So the noise shaper. What is a noise shaper? What happens with a noise shaper is it takes your 32-bit digital data, in my case running at 104 megahertz, converts it down to a level that can be used to switch individual switches, or in my case, individual elements within the pulsar array output. So you're converting 32 bits down to 5 bits. And it needs to do that so there's no change in performance in terms of the audio performance. One of the things that I noticed with the Dave project was that and this was really weird when I did my listening tests, my original noise shapers were 200 dB accurate. That's about 32-bit performance. And I found that if I improved the performance of the noise shaper, nothing changed. The instrument separation didn't change, timbre didn't change, the warmth and the smoothness didn't change. But one thing did change, and that was the perception of depth and the perception of detail resolution. And every time you increase the performance of the noise shaper, the perception of depth got deeper and deeper and deeper. Now, depth is a major issue with recorded sound. If you go to a cathedral and listen to an organ and you're 100 meters away from the organ and you shut your eyes, you can accurately position that organ to 100 meters very, very easily. If you listen to a dog barking a mile away, you know it's a mile away. You listen to it on reproduced audio, it's a couple of feet behind the loudspeakers. You don't get that perception of depth. And depth is something that's always intrigued me, right from when I first started playing around with audio. So having a mechanism that was linked to small signal accuracy, which is what this is actually doing, proved that the problem with depth perception is down to how accurate very small signals are being treated. What I failed to appreciate was if there is the tiniest error, and even if the error is at 0.0000001 dB, it doesn't matter how small that error is, the brain sees it as a truncation in depth, and that's really very, very weird. What I found with Dave was that you needed 350 dBs performance. That's a 64-bit level of accuracy. You can actually measure 350 dB performance when you're doing a Verilog simulation. So I can design my noise shapers and actually measure this performance, so I know it's accurate. What I've done with TT2 is because it's a bigger FPGA than the Hugo 2, I've got a much better noise shaper, and now we're looking at 100,000 times more resolution than before, which is an enormous number. An unbelievable number, and it's just amazing how sensitive the brain actually is to depth perception. So, output drive. You can have the best DAC in the planet, but if your headphone output drive is not very good, it's not going to sound very good. As you know, or you may well know, the principal architectural benefits that you have with my DACs is the analog section is very, very simple. It's only got one amplification section with one feedback network, 2 resistors and 2 capacitors. The reason it is so simple compared to conventional DACs is that it's an FPGA discrete DAC, so you don't have to worry about substrate noise, you don't have to worry about interactions within the chip, you don't have to worry about the reference being polluted, you can have discrete references, you can have everything being properly coupled. The other benefit is that the noise shaper runs at 104 megahertz. That's an extraordinarily high rate. Normally noise shapers run at 3 megahertz or 6 megahertz at a maximum. That means that my filtering characteristics can be very simple. Simple filter characteristics means a simple number of components. Simple number of components means better depth perception, better detail resolution, lower noise floor modulation. Depth perception, that was something I was talking about with the noise shaper. Something that's always puzzled me whenever I've done measurements with depth perception. You can hear differences in cables, you can hear differences in resistors, you can even hear differences on soldered joints. I always put these things down to small signal behavior, but was frustrated that I could never measure it. With the Dave situation, when I was doing 350 dB noise shapers, you can see why you'll never ever be able to measure it, because you need 350 dB accuracy to get the level where you can actually hear. So that was an interesting point. Anyway, getting back to output drive. I've got this second order analog structure. The benefit of the second order analog structure is it means that it eliminates the distortion in the output stage, and I'll be showing that later on the measurement section. We've also got much more capable output. So it's a very powerful output stage capable of delivering 5 amps of current. This means that TT2 will drive any headphone that you can imagine, most difficult headphones you can do, and it will drive loudspeakers directly, particularly efficient loudspeakers or near-field monitors. With the supercaps supply you with huge levels of dynamic current, so that when the loudspeaker requires dynamic current, the current is available for the amplifier. So, versatility. You can use it in pure DAC mode. You can use it with IEMs, even though we've got a very, very high level of output power, because there's a gain switch. So when you enable a gain switch, you can limit the output to 3 volts RMS. But what that also does is it reduces the residual noise down to 1.6 microvolts. That's actually the lowest residual noise of any DAC that I've ever designed before. So you can use it with sensitive IEMs, you can use it with extremely power-hungry headphones, and you can use it with passive loudspeakers. So measurements. Measurements are very important to me. That's partly because of my background of semiconductor design. These large semiconductor companies, they don't care about sound quality. All they care about is measurements. Projects are defined in terms of measurements, and you have to justify what you're doing in terms of measurements. So that's a discipline that's been embedded into me. Also, my approach is very scientific and rational. If I can hear a difference, I need to understand why that's making a difference. And if I can get a number out of that understanding, that helps my ability to make improvements. So it's a way of progressing. So I progress very rationally and scientifically. So objective measurements tell you what's going on. Well, they give you one indication of what's going on. The problem with measurements is that you've got to make sure you're measuring the right thing, you've got to make sure your kit is calibrated, you've got to make sure that the conditions it's being operated on is correct. And it's actually, measurements are not quite as easy as people may think they are. Distortion. We're looking at 4 zeros, 8% at 2.5 volts into 300 ohms. 3 zeros, 16% at 6 watts into 8 ohms. This is state-of-the-art levels of distortion performance for a linear amplifier. It's actually better than linear amplifiers, but this is with a DAC coupled to it as well. Single-ended output power, you're looking at 7.3 watts into 8 ohms, and we're looking at 18 watts using the XLR outputs. So did you say you had a laser? Oh, you gave it to me. Sorry. Okay. So this is the jitter performance. This is a standard J-test that people use to measure DACs. Noise floor is at minus 170 dB. There's nothing there. There's a faint trace of 50 hertz. That is on every single time I use the APX555, and that's the A to D converter within the APX555. But there's no jitter there. There's nothing there that you can see. So noise floor modulation, this was something I was talking to you about earlier, saying how important it was subjectively. Here's the measurement proof. Now, this is 2.5 volts RMS into 300 ohms. The distortion harmonics are below minus 130 dB. This is with the 2.5 volts signal, and this is with no signal whatsoever. And the noise floor is exactly the same, irrespective of signal being switched on and off. Regular DACs, you'll be looking at a noise floor that's generally about minus 170, and it will pump up to, a good DAC will be about minus 150, a poor DAC will be about minus 130 dB. So achieving zero measurable noise floor modulation which happens with Mojo, it happens with all of my DACs, is actually quite radically different to everybody else's DACs. And in fact, Jude from HeadFi was telling me he was measuring lots and lots of DACs. And he said the only DAC I've ever measured that has 0 noise fill modulation is from Chord. Distortion into 8 ohms. So here we've connected an 8 ohm load. This is at 6 watts RMS. Again, no noise fill modulation. The distortion has increased, but it's mostly the second harmonic that's gone up. The second harmonic actually doubles when you connect up an 8 ohm load. This is extremely low levels of distortion for a power amplifier. Now this was a test I actually did on Wednesday, and it's something I don't normally do, but I thought it was so cool that I ought to publish it. This is 8 ohms, 20 hertz, 12 watts using the balanced outputs. The distortion level was, I think, 0.002%. But what you can see, and what's interesting about this, is that above 3 kilohertz, there is absolutely nothing. No distortion components, no anharmonic components, no noise fill modulation, nothing. That is an extremely unusual result for a power amplifier, let alone a DAC. The reason why it's unusual is that this proves that there is no crossover distortion in the output stage. Because if you had crossover distortion, you'd have higher order harmonics going up to infinite frequencies. So this shows that the distortion just falls away to nothing, and it's actually going away somewhere like this, way below the noise floor. And having a distortion harmonics below minus 180 dB is actually I was quite amazed by these numbers coming out. It also gives an indication why TT sounds so smooth and natural, because it hasn't got these high-level harmonics. Okay, so just to wrap this up, TT2 sets new standards for measured performance, and you can see that from the slides I've just given you. It's the new reference standard for driving impossible headphones, and you can do it with efficient loudspeakers. And when you hear it with loudspeakers, that direct connection from the digital domain to the analog domain, and only 2 resistors and 2 capacitors, you hear something you've never heard before from power amplifiers. The depth and the detail resolution and the transparency is just quite extraordinary. This gives us an inkling for what's going to happen when the power amplifier project that I've been working on finally comes through to production. And the supercaps power supply gives huge dynamic reserve powers, as well as with the inductive filtering that I've put on the supercaps, I eliminate all the problems from the power supply that comes through. So when I plug the power supply in and off, and it will last, TT will last for 10 seconds, you can see there's no change in measurements at all when you plug the power supply in and out. So now's the time for some questions. I think we've got maybe a minute or two. So quick question, anybody? Yes. Ah. Thank you.
See, as much as the DAC development has progressed, assuming that a lot of the CDs that will be playing could have came back as far as 84 whatever.
Yeah, yes.
Were the professional analog to digital converters used in studios and such of adequate quality to still hear these benefits, or is it a case of maybe like CDs that have been produced in the last 5 years?
Actually, the opposite is true. I find the best recordings are ones that were made in the 90s. Modern A to D converters are chock-a-block full of aliasing. They use half-band filters, and it's full of aliasing issues. What those do is stop the perception of that sharpness when you hit something hard. So if you're doing a rim shop on a drum kit, for example, it sounds very sharp. When you play that through a modern A to D converter, it sounds soft, unnaturally soft. If you play it through a 1990s A to D converter, it manages to capture that transient information more accurately. And it's because they tended to use analog filters that had very, very good stop band performance and no aliasing issues, rather than using modern day delta signal and using that create half band filters that create lots of aliasing. My Divina A to D converter project, which has been sitting on my shelf for the last 6 months waiting for me to test, will it solve that issue? And it's going to be rather exciting when I get that to finally work to see whether we solve this issue of not being able to reconstruct hard-edged transients properly and accurately enough. So my favorite recordings are actually 1966 Deckers that were mastered in the 1980s and the 1990s. Because they can manage to reproduce kettle drums really accurately, and you get a real sense of the power of a kettle drum. If you listen to a modern recording with kettle drums, they don't actually sound like kettle drums at all.
So would you generally seek out the versions that haven't been digitally remastered then?
Yes, I don't like
early transfers.
The early transfers
Yeah.
I find as being the best. But
that's good to know that you still would get benefits of this new
Oh,
DAC
absolutely.
technology even with older.
Absolutely.
Yeah.
And my lecture tomorrow is about the M scaler when I'm talking about the million tap length filter. And this reconstructs things to a 16-bit accuracy. And you can hear the difference on modern recordings and MP3 and very old recordings. You can still hear the changes that when you get this reconstruction to this level of accuracy.
Well, thanks for answering that. It's good to know all the old back catalogues
Yes,
aren't worthless.
oh yeah, some of my favourite recordings are from the 50s and the 40s, but even mono recordings. But that's because of the musical performance rather than anything else. And somebody else was asking a question. Oh.
If you look at the digital representation of the audio signal, are all information in that digital source, or some room for interpretation?
If you go back to sampling theory, if you have a bandwidth limited signal that's being sampled, then all of the information is encoded within that signal. And the interpolation filter is not creating more information. It's not creating missing wiggles in between one point and the next point. What it's doing is that it's ensuring that the accuracy of the reconstruction is so that there is no variation from one sample to the next sample in terms of timing. So it's not about creating new information. It's about ensuring that the information that is there is not distorted. And it's about reconstructing the timing of that information so that it's perfectly done.
Comparing to the Dave project.
Yes.
Um,
This doesn't sound like a Dave.
No.
Unfortunately.
Sure. But it beats it in any discipline, or
It beats it in driving loudspeakers directly. Certainly my BMW 803 D3s, the Dave sounds shit driving those. But the TT will drive it because it's got more power. But if I use very efficient small loudspeakers, the Dave beats it in terms of depth and transparency and detail resolution. And it beats it by quite a big margin. And it's actually a little bit of a puzzle to me because the difference is bigger than I expect it to be. Because now I've got noise shaper performance that is very close to Dave's performance. And that should equalize my hope was that it would equalize the depth of performance, but it hasn't. So there's extra things going on within Dave that I cannot do because of cost limitations that's in TT2. But why it's interesting to me is I'm not quite sure where it's coming from. And if I'm not quite sure where it's coming from, that gives me the opportunity to make it better. So perhaps there'll be ways in the future of making a better version that exceeds Dave's performance. So that's why I'm intrigued by not quite understanding where this benefit is coming from. Okay, I think we better wrap that up. Thank you very much. Thank you.